Alright, so in this video I'm going to be talking about, I'm going to be going over pages 10 and 11 in the notes packet. This is where we are solving for n, so we're doing geometric sequences and we're solving for n. Before we get started, I want to note that there were some corrections to this page, so your page may look differently than what you see here. I want you to take a second, if your page looks differently, to write what you see here instead of what's on your page. The first change that happened is there. So whatever it had before, make sure that it says this now, just scratch it out. If you want a fresh printing of this, I have copies. I apologize for the mistakes. The second change is here. And then the third change is right there. So just if you have an outdated copy, scratch those out, try and make them fit what you see here, because this is accurate. And with those corrections out of the way, let's go ahead and get started. So what we've been doing recently is where you'll have a given value for U1, you'll have a given value for common ratio, and you'll have a specific term in the sequence that you want to find, and you'll plug all those in to get UN. But we've also seen some cases where you have U1, you have R, you have a specific value that it wanted to be equal to, and you need to figure out what term in the sequence is going to be equal to that. You need to solve for n. And that's tricky because n is in the exponent, so we can't just do addition, subtraction, multiplication, and division to solve for it. We need to use other methods, and that's what we'll talk about here. So we're going to go over 3 methods. First one being brute force, second one being graphing calculator, the third one being logarithms. And we're going to explore this in the context of this problem here. So at the start of spring, a pond has 15 lily pads on it. Each week, the number of lily pads doubles. If the pond has room for 780 lily pads, how many weeks will it take for the entire pond to be covered in lily pads? So you may notice here that we have something different. We have a U0. And the reason for that is because we want n to represent the number of weeks since the start of spring. So at 0, right, when spring is just starting, there are 15 lily pads. After 1 full week of spring, so at the end of 1 week of spring, there are 30 lily pads. At the end of the second week, it's doubled again to 60. At the end of the third week, it's doubled again to 120. At the end of the fourth week, it's doubled again to 240. At the end of the fifth week, to 480. And at the end of the sixth week, it's going to be 960. And so we can see from this that you're going to hit 780 during the 6th week, right? So you're going to finish 5 whole weeks, because at the end of the 5th week, you're going to have 480. But by the time that you finish that 6th week, you will have 960. So it'll be 5 point something weeks during the 6th week is when you'll hit it. So that's one way that you can solve it, is just by plugging in the numbers and figuring it out. The other way that you can do it is with your graphing calculator. So once we've kind of figured this out, again, figuring out that U1 is the number of lily pads after 1 week, we know R, well, we can plug those in over here, and we can say that UN is going to be equal to 30, right, the number of lily pads after 1 week, times our common ratio 2 to the n minus 1. All right, and now we can solve that using the intersect function in our calculator. So this is the same thing that we were doing last unit, where we can now go to y equals on our calculator. We know that function for calculating any term in our sequence. That function we just found to be 30 times 2 raised to the x minus 1 over, and then we want to figure out when that's going to be equal to 780. So we can do second calc, intersect, there's our first curve, there's our second curve, guess, and press enter. And we can see that the intersection is 5.7. Yep, so it's going to be 5.7 weeks. We're going to finish 5 whole weeks. During that 6th week, that's when we're going to hit 780 lily pads. So there's another way that you can do that. The final method is with logarithms. So this is the most direct method. So the way that we're going to start is with our formula. So we just saw that un is equal to 30 times 2 to the n minus 1, or in this case 780 is equal to 30 times 2 to the n minus 1. And the first step we want to do is we want to divide both sides by 30. All right, so actually I'm going to do that down here. Just going to rewrite it. 780 is equal to 30 times 2 to the n minus 1. We can divide both sides by 30. Cancel there. We want to figure out what 780 divided by 30 is. Seven 80 divided by 30. So that's going to be 26. And we have 26 is equal to 2 to the n minus 1. Now we're going to take the natural log of both sides. So you get the natural log of 26 is equal to the natural log of 2 to the n minus 1. And we can use logarithm properties to take the n out of the exponent. And the way that that works is, if you have studied logarithms before, you may have learned that log of a to the x power can be written x times log of a. Right? Whenever you have an exponent, a logarithm with an exponent inside of it, you can move the exponent out in front and turn it into multiplication. Right? That's a logarithm property. We'll be covering it more in depth later in the course, so if that doesn't make sense to you right now, don't sweat it. We'll spend more time with it later. But what that lets us do is it lets us take n minus 1 out of the exponent and put it out in front. So that will give us ln 26 is equal to n minus 1 times ln 2. And now that we've removed the exponent, now we can just solve for n. So now we're going to divide both sides by ln 2. And that gives us ln 26 over ln 2 is equal to n minus 1, or n is equal to ln 26 over ln 2 plus 1. Now if we go back to our calculator, we do ln 26 over ln 2 plus 1 and hit enter. We see that we get that 5.7 number, the same thing as before. So that's the third way that you can do it. All right, and let's see a tangible example of this. So the population of goats on an island starts at U32, or starts at 232. So because it's starting there, the 232, that's your U0, right? That's tricky. That's your U0. The population is expected to increase by 15% each year. What is the value of U1? What is the value after it has increased by 1 year? That's going to be 232 times 1.15. We do that. 232 times 1.15. After 1 year, there are 267. Goats on the island. Oh, sorry. Skip the question. So 267 goats on the island after 1 year. Sorry, U1, because remember, we want n to represent the number of years since the start. And then what is the value of r? Well, the value is r. That's what we're multiplying by each year, so it's 1.15. So let's create an explicit formula here. So it's going to be un, the number of goats after n years, is equal to the amount of goats after the first year, 267, times our common ratio, 1.15, to the n minus 1. So using our geometric sequence, and now we just want to plug in 10 and 20 because we're asking for after 10 years or after 20 years. So we can go 267 times 1.15 to the 10 minus 1, and 267 times 1.15 to the 20 minus 1. We can plug those into the calculator. 267 times 1.15 to the 9th, 2.67 times 1.15 to the 10th, or sorry, to the 19th, 20 minus 1. Oh, not 2.67, sorry, 267 times 1.15 to the 19th. There we go. All right, so now we can see that after 10 years, there'll be 939 goats on the island, and after 20 years, there will be 3,800 goats on the island. All right. And now we want to use one of any of the three methods we just went over to determine how many years it will take for the goat population to reach 15,000. So I'll model how you can use any of the three methods. The first one for brute force, you could definitely just go through, right? So we know after 20 years, it's at 3,800. So we might say, well, what about after 25 years? Where are we? 8,000, or sorry, that would be after 26 years because it's n minus 1, but you get the point. Then, okay, that wasn't enough. What about 28? No, not quite 28. What about 29? And now we see, okay, so now we found one value below 15,000, right? We see when n is 29, meaning our exponent is 28, we have 13,367 goats. But when n is 30, it rises to 15,372. So it's right during that 30th year that it's going to hit 15,000, right? You're going to finish 29 whole years. You're still not going to be there. During that 30th year, before you finish that 30th year, that's when the population is going to hit 15,000. All right, and let's see if we can do that the other way. So let's plug our function into our calculator here, just like that. And now in y2, we're going to want to put 15,000. And then we want to do our intersect function. And if you get this, I find that generally means that your window is not big enough. So here I'm just going to change my window a little bit. I'm going to make my x max 40. I'm going to make my y max. Sorry, I'm going to make my y max 16,000. That way, if we graph them, see now we can see the whole function. And now when we go to intersect, you'll be able to find the intersection, which again we found is 28.82. You finish 29 full years. During that 30th year, that's when you hit 15,000. Okay, and then the final method, I'll show that this can work with logarithms too. So we have 15,000 is equal to 267 times 1.15 to the n minus 1. We'll start by dividing both sides by 267. If we do 15,000 divided by 267, we get 56.2. And that's equal to 1.15 to the n minus 1. That means that the natural log of 56.2 is equal to the natural log of 1.15 to the n minus 1. Using our exponent properties, that means that the natural log of 56.2 is equal to n minus 1 times the natural log of 1.15. divide both sides by ln 1.15, and you get n minus 1 is equal to ln 56.2 over ln 1.15, meaning that n itself is equal to ln 56.2 over ln 1.15 plus 1. And if we go back over here, we get ln 56.2 divided by ln 1.15 plus 1, and there's our answer. All right, so let me know if you have any questions on that, and I apologize again for the mistakes. Hopefully they don't cause too much confusion.